Okay, so hi everyone. So yeah, my name is Antoine Godet. I'm the research associate in charge of the Gold Window thematic project. So yeah, I divided this talk in two parts. First, I will give you quick updates about the project we started last year. And in the second part of the talk, I will talk about more about the research we've done on the plutonic rocks from the Pontiac subprovince. So as you know, this is a project that involves a lot of people, so different professors from Laval University, as well as different PhD students, different research associates too, and people from Laurentian University, people from Europe, from UBT, for example. So just a quick remind. So what are the main objectives we are trying to and the main questions we are trying to answer for the next 4 years. So it's basically if we take a potential rock source, namely a metasedimentary rock, and we try to decipher the PTT history of that rock, we'll be able to find eventually if those rocks were the source of fluid, ligands, and gold in the superior province. So the first objective is to test the hypothesis that fluid, gold, carbon, and sulfur were derived from the metasedimentary provinces. Second one is define quantitatively the pressure, temperature, time, chemistry, deformation, evolution of those provinces. Then we aim to better understand the Neoarchean geodynamics and the impact of regional fluid generation and the circulation of gold endowments. Characterize the mobility of key elements during prograde metamorphism. And finally, at a smaller scale, characterize the source and mobility of those elements at the mineral scale. So who is doing that? Actually, there are 3 PhD students. So Isaac, who's done last Friday, who's presented to you last Friday, his PhD project. And right after me, there's going to be a talk from Adrian and Diogo, who are the other PhD students, and myself. And yeah, I wanted to highlight that we want to compare well-endowed areas like the Pontiac subprovince to less endowed areas like the Quetico. So just a bit of what we've done so far. So we've been able to go on the field. So we've accomplished 2 field seasons, 2020, 2021. And we've accomplished the compilation. We've done some chemistry in situ, holochemistry, using the laser, the microprobe, the micro XRF, but they are still coming up. We have new ages about uranium lead, and also lithium and garnet, but more are coming in the next year. And Diogo performed the preparation of the samples for the ultra-low detection limited holochemistry. So the next step is going to be pursue the phase requirement modeling, pursue the chemistry, and we're going to start the writing of the 2 first papers. Okay, so now I'm going to move on to the second part of my talk, which is about the Neoarchean thermal history of the Pontiac subprovinces. And specifically, we took a look at the Petrogenesis of the Granitoids. So if we look at the geological map of the Pontiac subprovince, you're going to see that in pale blue, you have all the metasedimentary rocks, but there are a large amount of granitoids that outcrops in the subprovince, including the big Dussel batholith, which is in red and in that map and pink, but also different smaller suits like the Lac Fréchette, the Rimini batholith, and the Lac Fournier Pluton near Malartic. But actually the source and the timing of those different plutonic suites is probably constrained. So the questions we want to address is first, what is the impact of the magmatic intrusions on the gold fluid window? What's their synchronous magmatism during prograde metamorphism? So we're going to compare the uranium-lead data from the metasedimentary rocks with the plutonic rocks. So we're going to have a direct comparison. Next, what kind of magmatism in what tectonic environment? So that involves holochemistry, trace element chemistry, but also zircon isotope chemistry. I'm going to show you that in a couple of seconds. And finally, what is the proportion of magmatic volatiles inside the metamorphic background? So trying to evaluate the stable isotopes chemistry. So today I'm going to focus on three main parts. So first, I want to talk about the opacitic agnates. As you see on this picture, those are tonalite dioritic gnases. We don't know the age at that time, and it is what we know is that it's cross-cut by a pink granite or pegmatite that have been dated at 2660. So we decided to sample that and have a look. Secondly, we decided to sample all the monzonitic or monzodioritic plutonic suites. So it involves the Lac-Fournier Pluton, it's been dated at 2682 by teams, but also the Lac-Fréchette Pluton, dated at around 2680, 2685. And finally, the Lac-Rémini Pluton, also dated at 2670 to 2680. So we decided to sample those guys again. And also to take different samples from the Decel batholith, which is muscovite plus or minus biotite plus or minus garnet-bearing granite. And it's big dated, but it's poorly known actually, consider the size of that big batholith. And it's been dated between 2668 to 2640. But just on a couple of grains, monazite and zircon. So what about holochemistry? So it can be divided in three different parts. So we have if we look on the top right of that slide, we can see that it can be divided on three different major groups. So the first one are the Granitoids, so involving the Lac-Fournier, Lac-Fréchette, and Rémini batholith. The second one is the Decel batholith that basically falls into the micas granites in that classification after Laurent et al. And finally, the opacitic agnates falls into the TTG or the more hybrid chemistry. We can see that the Granitoids are more metaluminous. The S-type granite, namely the Decel batholith, is more peraluminous, but also more furan. Now, if we move on to the uranium-lead dating, so we targeted zircon, monazite, and titanite. We were able to recover the zircon and titanite from the opacitic agnates, the same for the Granitoids. And from the S-type, only monazite was datable because zircon was basically metamict. Then we applied strict filtering to keep the pristine grains. So just an example, here you can see this is the age in the x-axis. And then you have the 204 lead, and you can see that there is a deviation or a spreading. So we did apply a threshold to keep the more pristine grains. And we also filtered by low strontium, low calcium, and low titanium. So those are just examples of cathodoluminescence images. So here from the Rémini batholith, which is a Granitoid, you can see oscillatory zoning. And like I said, the zircons from the Decel batholith are more metamict, really rich in uranium, couple of thousands of ppm of uranium. But when you apply a strict filtering, you can end up with nice data. And for example, in that case, 10 out of 50 analysis. And if you look at the trace element content of the data, it's really similar. So we can assume that they represent the same generation. So those are the results. So we have new dates, new ages from the different plutonic suites. So we have the first age at 2765 for the opacitic agnates in gray. Then we have new ages at 2680 from the Lac-Fréchette Pluton. Again, same age from the Rémini batholith. We did confirm the age from the Lac-Fournier at 2680. And then we have different ages from the Dessel batholith. I'm gonna develop that a bit. Quick words about zircon trace element chemistry. So if we look on the top right of that slide, we can see that the epsilon hafnium values fall nearby the depleting mantle for the sanukitoids and the TTGs. And applying those criteria, we can have an idea of the oxidation state and the hydration state of the source. And we can see that all the sanukitoid seems to derive from a source that is considered more oxidized and hydrated, actually. It fits the molecular database. And unfortunately, we don't have any data to compare with from the Dessel batholith because of that, those icons. Okay, so to illustrate all the new ages we have, I decided to plot them. So this is the age, young is at the top and old is at the bottom. So first we confirm the 2680-ish ages of the sanukitoid suites, which is nice. Then we have the first age of the opacitic agnase at 2765. And as you can see for the Dessel batholith in green there, it's a bit more complicated. So to illustrate that, I decided to plot all the concordant dates we have from 3 samples from the monazite, so almost 50 grains. And we can see the distribution of those individual dates. And we can see that, you know, we started to have a record at 2680 down to 2615. So it seems that it might reflect a protracted magmatism with maybe 2 apparent pulses at 2640 and 2620. So it's more complicated than just one crystallization history for the Dessel batholith. One thing to note is that if you look at the microstructure of the Dessel batholith, we can see like bulging or subgrains, so it's been deformed, and this is really important in the history. So we can highlight that at the thin section scale, but if we look also at the map scale, like I did there, you can see that, you know, the contact between the Dessel batholith and the other bodies or metasediments seems to be folded. And we can, you know, start to think about drawing a crenulation orientation there that seems to fit the S4 as compiled by Pierre Baudot and co-author, which is oriented north, east, southwest. So we might have the first constraint or maximum age of the late D4 deformation because the Dessel batholith is deformed. So I used the compilation of the plutonic and intrusive rocks after moletals, and I color-coded it with chemistry. So in red you have the TTGs like, in blue you have all the sanukitoids like, and in green you have the S-type granite. So first we can see that the sanukitoid seems to fit what has been dated in the IBDB subprovince. And it's the same for the Pontiac, for the S-type granite. And the opacitic agnase seems to be quite alone in that compilation, just based on the plutonic and intrusive rocks. If we compare nearby the Pontiac subprovince, and we look in the Valdor camp, for example, and in the Rwanda camp, we can see that the sanukitoids were intruded, were seen to the maximum depositional age of the Pontiac. We can also try to compare that with the new dates from Michael Herzog, who presented last Friday, and those are the new ages he got. So we can see that, you know, it's a quartz carbonate tourmaline vein seems to fit the 2640. So something was happening at that time. Thermal pulses or deformation. That's why they proposed to extend that D2 or D3 deformation event. And then we have something like 2620. So we might think about, you know, putting a maximum age of the D4 deformation event that could be synchronous to the gold remobilization. And finally, I want to focus on the opacitic gneiss, because David Moll and co-author proposed that in their model, the Opatica crate, the Opatica subprovince was basically rifted and open and to intrude the IBTB subprovince as a whole. But they were missing that Opatica-like ages in the source of the IBTB. And we might have the first occurrence of 2670-ish dates south of the IBTB. So the Opacitica could actually be the Opatica and represent the basement of the Pontiac subprovince. So to conclude, and the take-home message for you today, so we presented new holochemistry from the different plutonic suits in the Pontiac subprovince. We acquired new uranium data and trace element on zircons. It seems that we have Opatica-like basement south of the IBTB subprovince. Seen depositional salinity magmatism from an oxidized and hydrated source. It seems that the history of the S-type magmatism seems to be long-lived, at least for 40 to 50 million years, with two apparent pulses at 2640, 2620. And we might have the first timing constraint on the maximum age of the D4 event at 2620, question mark. Thank you.
Great, thank you very much. We have time for questions.
I'll have a question, Antoine. A good way to strengthen your argument about the 2620 being meaningful in terms of the D4 event would be to go and look at the contact between the Decel batholith and the Pontiac sediment turbidites, because you have a big strength difference between those two rocks. And what we know of that D4 events is that it gets localized. So you would expect to see evidence of dextral shear along that contact. So that would be a test on your interpretation.
Yeah, that's a good one. The contact is not always easy to find because of exposure, obviously. But we've been able to find, really decimetric to metascale or decimeter scale enclaves of the metasediments from the Pontiac group. They seems to be always deformed, so it was in place post main deformation of the Pontiac. But regarding the D4, it's a bit more tricky. But yeah, I agree with you. Targeting that could be a good idea. Looking at the contact for sure.
Antoine, we have one more question. Pierre Simon has a question.
Yeah, sure.
Yeah, hi, nice talk. I'm very interested by this old age for the Opacitica gneiss and the idea that it might be the equivalent of the Opatica province. How widespread is that unit? Is it a big thing or just a local unit?
Well, so you see it. It's a gray thing there, and so there are not a lot of outcrops. We were not able to find a boat to look in the big lake there, the Opacitica lake. But no, it's not that big. So why is it exposed there and not somewhere else in the Pontiac? I don't know.
Yeah, but there's some old cross that was there before all these intrusions arrived. So maybe it goes underneath. All right, I'll be in touch with you about that. Very interesting. Thank you.
Sure.